Hello, I welcome you all in this presentation related with the subject materials processing fundamentals and practical, and we are talking about the practical and lab demonstrations related with the subject materials processing. And in this particular presentation I will be talking about the gas welding and gas cutting of the steels. So wherein we will try to learn about the many things, say different system components which are used for the gas welding. These are particularly cylinders for fuel gas as well as for oxygen. Okay. Then we need pressure regulator to supply the oxygen and acetylene or fuel gas at a particular pressure. Okay. Then we need control device like welding tractor. Okay. This will allow us to use the system to move the system at the desired speed for effective welding or cutting. Okay. Then depending upon the type of metal, you see we use the flux also for cleaning and developing the quality weld. Then we can also use the suitable filler for the development of the weld joint. So welding torch is different from that is which is used in for cutting, because in cutting we use the multiple the orifices or holes through which the flame gas will be developed, and then at the center there will be a hole through which oxygen is supplied for the cutting purpose. So this flame is particularly used for preheating the metal up to the kindling temperature or oxidation temperature. But in case of the gas welding, the heating of the metal is done up to the melting temperature so that the fusion weld joint can be developed. Okay. So as far as the system components are concerned, these are the main parts. Then selection of the welding torch nozzle. So depending upon the thickness of the sheet to be welded, the different nozzle sizes are used. Then the different types of the flames which are developed, like it can be oxidizing, carburizing or neutral flame. Depending upon the purpose and application, suitable type of the flame is developed by adjusting the oxygen to fuel ratio. Then we will see the demonstration of the gas welding and the gas cutting operations. And when the weld joint is developed or the cutting is performed, like say this is the plate which is cut along a particular line like this. So when the cut is made, we will try to study the cut surface with regard to the surface roughness, microstructure, hardness distribution, compositional variation if any is taking place due to the cutting, or the kind of the drag or the surface features that are produced in the cut edge surfaces. So here as far as what we use for the development of the weld joint, like oxygen and acetylene cylinder, pressure regulator, flux for removing the impurities and forming slag, for developing the sound and clean weld joint, then parent metals for the welding purpose, and the gas welding torch of the suitable nozzle size, the welding tractor for controlled movement of the flame, and then performing the gas welding or the cutting as per the operation. And whatever the weld joint is developed or whatever the cut edge is prepared, cut surface is produced, that has to be prepared by grinding followed by polishing and then etching for microscopy, and then optical microscopy is performed and microscopic images are captured to study the microstructure, and the cut edges are also subjected to the hardness study and the surface roughness study, compositional variation using the optical emission spectroscopy. The different things are characterized as far as the cut edge is concerned to assess its quality. So now in the following section, we will be trying to see the demonstration of the gas welding and the cutting. Hello, dear students. In this video, we will be talking about the gas welding and its the setup and the methodology how it is done. So in general the process is called oxy-fuel welding, which is can be used for cutting, joining and the brazing also. So the principle used here in this process is very simple, where one fuel gas which may be in form of propane, acetylene, hydrogen or similar kind of the gas is used, uh, and it is mixed with the oxygen to have a combustible flame, and that flame is used for the purpose of heating the base metals in case of joining, heating in case of the cutting. Means heating in cutting primarily involves the oxidation. Uh, First of all heating, thereafter followed by the flow of the high pressure jet of the oxygen for the cutting purpose. So, here you can see so we need to supply both oxygen as well as acetylene, and both are mixed in a particular proportion in order to get the flames of the different types, so that they can be used for joining as well as cutting as per the kind of metal which is to be processed. So, if we see, this is the torch which is which will be used for the cutting purpose, and here we can see there are two pipes. The one you can see, one is blue and another is red. The one which is red is for the supply of the acetylene or fuel gas, and the blue one is for the oxygen. And here both will be fed, and in this mixing chamber both will be coming, and the proportion of both the gases can be adjusted using these two control valves. Okay. So, you can see here one is coded with the blue and another one is with the red. So, these knobs are in order to adjust the supply of the oxygen as well as the fuel gas, and that mixture of the oxygen and fuel gas will be coming through this nozzle outside, and then using this kind of the lighting system, it gives the spark. So, the fuel gas mixture is burned, and then through the adjustment of these knobs, by changing the proportion of the oxygen and acetylene, suitable different types of the flames are produced. And most invariably, the gas welding can be autogenous or it can be with the help of filler. So, if the filler is to be used, then filler is just like simple steel which is copper coated in order to avoid the rusting, and so the fillers of the different sizes and the diameters can be used as per the need of the joining. Okay. So, as I have said that oxy fuel gas system can be used for the joining, brazing as well as cutting. So, here if we see, this is the you can say the tabular data about the kind of parameters which should be used for oxy fuel cutting or oxy-acetylene cutting purpose of the different types of the steels. So, these are mainly structural steels which are cut. So, you can see the steel plates of the different thicknesses, the kind of nozzles that nozzle sizes that are to be used, like 1 by 32 inch, 3 by 64 likewise. So, these are increasing diameter of the nozzle, so that your the flame size is bigger and it is able to deliver more amount of heat required for the preheating of the steel while cutting. And you can see these are the kind of oxygen pressure which is used for the cutting purpose. You see, once the preheating part is over, kindling temperature has been attained, then we supply the oxygen jet, so that oxidation can take place and exothermic reaction results lot of heat generation, that in turn facilitates the melting and cutting of the plates. So, this is just a broad guideline for cutting the different steel plates using the different oxygen pressures and the nozzle sizes. So, here we can see in this is the list of the different items that we need for the gas welding or the cutting, like it includes acetylene cylinder, oxygen cylinder, which are the main gases for oxy fuel cutting or welding. Okay. Then oxygen regulator, acetylene regulator, acetylene hose pipe, which is used for taking the acetylene from the either cylinder or from the source to the nozzle. Similarly, the oxygen hose connection, acetylene hose clips which are used for tightening purpose, then oxygen hose clips, blowpipe set, cylinder key, and then a spark lighter to ignite the oxy fuel mixture, and the gas welding goggles to protect the eyes from the radiations as well as the sparks, and the wire brush for the cleaning purpose, and the tongue for handling the plates which are to be joined. So, now in this the practical demonstration will be showing how to develop the gas weld joints in procedural way. What will be the first step, what will be the second step, how to develop the different types of the flame and how do they look like. Now, here onwards we will be giving the demonstration of the gas welding. So, now we will show the demonstration of the gas welding process. So, here we have fired the flame using the spark. So, now we will show that how by adjusting the control valves we can change the different types of the flame. Okay. So, this is like say the one type of flame where you can see just the two cones. Okay. One is the outer one which is considered as a low temperature zone, and another one is the inner one. Okay. Now, show the different types of flame first. Okay. This is neutral flame. Okay. Now, carburizing, can you switch over to carburizing? Okay. Yeah, so here you can see there are three flames. One is outer, then intermediate, and then the inner cone. That's very clear. So, the intermediate feather or the flame is an indicative of the proportion of the acetylene. If we keep on increasing the proportion of acetylene, then intermediate feather will keep on increasing in length. Okay. Now, we'll show the like neutral flame. You can go for the neutral flame. Okay. Now, we'll show the welding, how procedurally we can do the welding. Okay. In one side we have filler, another side we have flame. This is at 45-degree angle of both the torch, the flame, you can say flame axis, and the filler axis. Okay. So, initially for the welding using the flame, we will be preheating the plates to be joined. Once the preheating is done to the enough high level temperature, wherein little fluidity is established along the edges, the filler wire is fed in the flame zone. Both are almost at 45 degree. Okay. This is the preheating stage. Once the preheating part is over, the filler is fed, and then both the flame as well as the filler are moved along the weld line to complete the joint. And you need a lot of skill in order to control the feeding of the filler as well as proper manipulation of the flame, so that there is a equal distribution of the heat and at the same time desired penetration is also realized. This is more or less, can say the lot of skill is needed for proper control and manipulation of the gas welding. So, we will keep on feeding the filler wire along the weld line. You can see that both are inclined at a certain angle, which is usually 40-45 degree, and here in this case the torch is pointed in the direction of welding. So, that is suggesting the forward welding. In this case, the base metal to be welded is preheated by the flame itself. That helps to increase the welding speed as well as the penetration. And when the torch tip is inclined in the direction opposite to that of the welding, then we say backward welding. And in the backward or backhand welding, our post heating of the weld joint or weld metal is realized. That helps to relieve the residual stresses as well as soften the weld joint. So, this is how we can see the steel plates have almost been joined by the gas welding. So, on cooling, we can see the kind of the weld bead profile and the condition of the penetration. Okay. So, you can see the tongue is being used to manipulate, adjust the welded plates. Okay. And the smoothness of the bead profile to a great extent depends upon how effectively in control way the filler and the flame is manipulated during the welding. That is all from the demonstration side of the gas welding process. As far as cutting is concerned, gas cutting of the steel surface, the kind of process parameters which are used as like the oxygen pressure 5 bar, the fuel gas pressure 0.3 bar, then the torch travel speed is set at 2.5, nozzle to workpiece distance is 5 mm, and torch angle with respect to the surface of the plate which is being cut is 90 degree. Like say, so these are the the photographs of how the gas cutting is being performed and the curve is produced, okay, in these three cases. So, if we take any cut edge surface and try to see the curve width, what is that? Like say, this is the steel plate and cut has been made along this. So, the gap between the, so width of the cut is known as curve width. So, curve width indicates the kind of material loss that will be happening during the cutting. This is one of the performance parameter of the cutting. So, if you can see, if we take the readings of the curve width at the multiple locations, then it comes out to be like ranging from 2.15, then 2.1, and on an average the curve width is 2.19. Okay. So, this is one of the aspects related with the cut edge that is produced and the curve width. If the cut edge surface is subjected to the microstructural property characterization, then what we see, due to the heating of the cut edge up to the fusion temperature, then the other zones next to the fusion boundary, next to the zone which is subjected to the melting, they will also be experiencing the higher temperature. So, this is a cut edge. So, certainly this will be subjected to the temperature up to the melting point, but there will be other zones, those will be heated to the higher temperature. So, the zones, all the zones which are heated above the lower critical temperature, they will be experiencing the change in microstructure as well as mechanical properties. So, the zones which are heated above the above the lower critical temperature, experiencing the change in hardness as well as microstructure. That zone can be termed as the width of the heat affected zone. The width of heat affected zone can be characterized in number of ways, like say compositional variation, microstructural variation, or hardness variation. There can be different ways to assess and evaluate the width of heat affected zone. What it shows that in the zone next to the cut edge experiences many metallurgical changes, and the width of the heat affected zone, the distance up to which the changes in structure and properties take place, that width comes out to be during the cutting is like say 840 micrometer, 800. So, on an average this width is 852 micrometer, like 0.85 mm or so. Okay, that is what we can see. And as far as the hardness variation is concerned, the hardness near the cut edge or hardness of the cut surface is in the range of, say, if we measure the hardness changing on a, if we measure the hardness distribution increasing distance away from the cut edge, then at the cut edge it is maximum, like say 185, 185, and then it is decreasing gradually. Okay. So, 153 for the base metal, and near the cut edge it is higher. So, in all these cases near the cut edge hardness is higher, and on at the distance away from the cut edge the hardness is lower. So, that indicates near the cut edge the hardened phases are being formed, which may be in form of partial very fine grained structure, or it may be in form of the martensitic transformation, maybe partial martensitic transformation. Okay. So, so what we get basically near the cut edge hardness is higher as compared to the zones which are away from, like this. Here we have around 185, and away it is like say ranging from 140 to 150. Okay. So, this higher hardness near the cut edge is one of the negative aspects, especially in case of the hardenable steels, because they become crack sensitive due to the presence of the residual tensile stresses, especially during the welding. Like say this is the steel plate and it is subject to the cutting along this line. Steel plate will be composed of certain alloying elements like carbon, manganese, silicon, sulfur and phosphorus in case of the carbon steels, but if it is alloy steels, then other elements like chromium, vanadium, molybdenum can also be there. When the gas cutting is performed, what happens? The gas, during the gas cutting we use oxygen plus fuel gas. Okay. So, this oxygen, especially if there is unburned oxygen, that it tends to react with the alloying elements, and that tends to remove those alloying elements from the near cut edges. Okay. Say especially the loss of carbon takes place from the surfaces near the cut edges, and that we can say as a decarburization. Loss of carbon content from the surfaces next to the cut edge can occur, especially in the due to the presence of the oxygen. So, the top layer shows the lesser carbon content, as we can see, as compared to the base metal. So, although difference is less, say in on an average the top layer carbon content is 0.16, while the base metal is having say 0.174. So, the difference is of a 0.01%. So, here what we can see, little loss of the carbon from the cut edge takes place. If we try to study the surface roughness of the cut edge produced by the gas cutting, then it comes out to be like in the range of 2.16 to 3.94. Even very rough cut surface is also produced under the unfavorable cutting conditions. Another important aspect is the drag lines, like we can see here. These cut lines are vertical and then these tend to become slant as we go down. So, if we use higher cutting speed, then these drag lines become significant. Okay, and these tend to increase the surface roughness of the cut edges. Now, I will summarize this presentation. In this presentation, we have seen the different components related with the gas welding and gas cutting, and how the gas cutting affects the characteristics of the cut edge of the steel. Thank you for your attention.